All right. Polls coming up. Make sure you are ready to go. Just click yes once you are ready, and then we'll get started. All right, just another 30 seconds for people to get ready, and then we'll get started. Okay, looks like most people are ready to go. So, continuing on with Unit 3, we're now diving into graphing quadratic equations and solving things by graphing. And so, like, what information can we get? So when we are asking to solve quadratic equations, does anyone know what it particularly means to solve a quadratic equation? What does it mean to solve it? Any ideas?
To find h or t or
To find h of t, depending on what the question is asking for, that is true.
yeah.
But let's say we're not talking about like a specific question. Let's say I just like give you a quadratic equation. I'm like, oh, here's a parabola. What solve for this parabola? What are the solutions to this? Anyone have an idea? Because when I say solve or find the solutions to a quadratic, I'm specifically asking for something. It's already on the screen, by the way. If you look very carefully. When I ask for the solution for the equation, what am I asking for? The word solution is right here.
Solve for the variable.
Which variable?
The root of the equation?
Right. The root of the equation is what you're solving for, right? And the other word for root that we talked about yesterday was solution, as well as x-intercepts. Okay? So when I ask you to solve for a specific quadratic equation or any equation, any function in general, I'm specifically asking you to find the x-intercepts. Like, can you solve me the x-intercept of this function? So that's what I mean when I say solve this equation. Find the x-intercepts. Okay, so those are the roots that make it true, and so on and so forth. So we are looking for those roots. Now, of course, in the context of a word problem, you're solving for different things, right? And of course, you're going to answer the question depending on what it asks for. So we're going to go through a word problem within your textbook. So this is number 14 on page 142. So it says a ball is thrown into a water from a cliff that is 175 meters high. The height of the ball above the water after it is thrown is modeled by this function. So given here, h of t is equal to negative 5t squared plus 10t plus 175, where h of t is the height in meters and t is the time in seconds. So 14a, when will the ball reach the water below the cliff? Okay. So, and part B is when will the ball reach a ledge that is 100 meters above the water? So first off, when will the ball reach the water below the cliff? What is that asking for?
The time?
What the time and what's the height when it hits the water? What is the height when the ball hits the water for us if we were to
0.
visualize it on 0? Right? Because it says that the ball is thrown into the water from a cliff that is 175 meters high. So we're assuming that the height, right, is measured from the starting of where the water is, which would be 0. So we would say h of t is 0, and we need to solve for t. We don't know what t is, right? So that's our given, that's our unknown. So when we plug it in to our equation that's given above, right? So I'm just going to copy the equation here. When we plug it into our equation where h of t is 0, we're saying 0 is equal to negative 5t squared plus 10t plus 175. So that's what we're doing here. Now the question from here is, okay, we need to find where the height is 0. And we need to solve for t. We need to solve for all the t values that make this true. And the way you're going to do that is to solve for the roots of your equation, right? So we're solving for the x-intercepts using this information. That's going to give us our answers, all the x values that work. So here, if we factor this, because the way to get your x-intercepts is to factor, the first step is to common factor this. So we're going to common factor out. I'm going to common factor out the negative 5. So in doing so, we're going to get t squared minus 2t minus 35. Whoopsies. So that gives us, dividing everything by negative 5, gives us what's left inside the bracket. Then from here, we have to actually factor the quadratic. So this is definitely not one of the special cases, right? It's not a perfect square here. 35 is not a perfect square, and it's not difference of squares. And so because a is 1, we can just use our product sum method. So if we write down on our side here, like, oh, a is 1, b is negative 2, c is negative 35, ac is negative 35. Two numbers that multiply to negative 35 but add to negative 2. Anyone have the two numbers?
5 and 7.
5 and 7. Which one's negative? Which one's positive?
7.
7.
7 is negative, yes. 7 is negative, 5 is positive. So we're going to get t minus 7, t plus 5. So this is factored now. So what are our x-intercepts? What are the t values?
Positive 7 and negative 5.
Perfect. So we get t equals 7 and t equals negative 5. That's our two answers, right? When 7 minus 7 is 0, negative 5 plus 5 is 0. We set these brackets equal to 0 and solve for it. So when we do that, though, are both of these answers correct? So we get two answers, but are both of them right?
No, because it can't be negative time.
Bingo. You can't go negative time. If you were going negative time, we're assuming that the ball is going back in time and we're time traveling. So in the context of the question, because t is time, we can't go negatives, right? We can't go into the negatives here, all right? So as a result, t has to be positive. T equals 7. So therefore, we can write our final answer here. The ball reaches the water after 7 seconds. So that would be the answer to this one here. Okay? So this is how you would solve your answer for when h is equal to, or the height is equal to 0. Now let's try the second question. What if we're asked for when does the ball reach the height of 100 meters above the water. So a little bit different, right? The situation's a little bit different. But the way you solve it is exactly the same, but there's just one extra step in there, which is not overly difficult. So here, for question B, the height above the water that the question has given us is 100 meters. Right? So h of t is 100. That's what it's told us. The height is 100 meters. So we're still trying to figure out when, which is time. Okay? So our equation stays the same. So you'll notice the first three steps are exactly the same. What are we given? What's our unknown? What's my equation, right? The first three steps of my guess method. Once we get there, we plug in, substitute 100. And then we can solve for it, right? Now, from here, what do we do? In the previous question, it was 0. We could just factor it. But this one, I don't think it would work out very well if we just factor it right away. So what does anyone have an idea what we should do so that we can factor it?
Do we need to move 175?
Not the 175, but rather the 100. But you had the right idea. Instead of moving the 175, we're going to move the 100 over to the other side so that the left side does equal 0. And we can then write negative 5t squared plus 10t plus 175 minus 100. And so our new equation that we're going to factor is this one here. We now get negative 5t squared plus 10t plus 75. From here, to solve for t, when we're solving for t, we have to factor it. So we're going to factor this. Same thing, we're going to common factor first. So we get t squared minus 2t, and 75 divided by negative 5 is negative 15. And then, now we have to factor this one here. So a is 1, b is negative 2, c is negative 15, so ac is just negative 15. Two numbers that multiply to negative 15 but add to negative 2.
Negative 5 and negative 5 and 3.
Negative 5 and 3 is correct. So negative 5 times 3 is negative 15. Negative 5 plus 3 is negative 2. So we're going to get t minus 5, t plus 3, which means the answers that come out of it are the opposite signs. So t equals 5 and t equals negative 3. But we already know we can't have negative time. So therefore, the ball reaches 100 meters above the water after 5 seconds. And that would be your answer to question B. So notice how the process is still the same. The only step that has changed is that when we set it equal to 100, we just want to make sure that everything is on one side. So we move the 100 to the right, and we set it equal to 0, and then we factor it, right? So whenever the question asks you, solve for time, when you're solving for the variable inside your equation, you want to factor and solve for those variables. That's going to give you your answer here. I'm going to let people copy this, leave it on the screen. Does anyone have any questions about these two things that we just calculated here? So most of you should be fairly good with factoring and stuff like that. So I think that's okay. Okay. Let's move on. So then, for problem solving here, so it's important to understand the meaning of like different solutions to quadratic equations, right? What do these x values mean? What do y values mean? What do the solutions mean, right? So if I ask you like, what does this point represent? For example, like, oh, it's asking for like what's the vertex? And I ask you, oh, what's the vertex? And then you give me the coordinates. And then I ask you, what does that represent? And the answer I get is that's the vertex. I'm like, no, that's not what I'm asking. Like if I'm asking, for example, a baseball is thrown into the air to catch, right? And then I ask you, what's the vertex? And then I ask you, what does that vertex represent? I'm asking you, what does the vertex mean in context of the word problem? So if it was a baseball being thrown, I'd say the vertex is where the maximum height of the ball and the time it takes to get there, right? That's what the vertex means. So when I ask you to explain or what it represents, I'm asking you, can you kind of translate this into the context of the word problem? That's what's important, right? Can you really understand what it is? Can you take it away not just from a math context point of view, but a regular point of view? Like when I talk about parabolas, often if you play any sports, you know this in a very primal sense, or not primal, primitive sense. Sorry. And what I mean by that is that when someone kicks a ball or throws a ball or anything like that, if you are at least somewhat athletically capable, in other words, you can catch a ball, right? Hopefully, if you can catch something, then you have that primitive understanding of a parabola. You know where the ball is going to go, and you know when it's going to fall and where it's going to fall, right? So you have this understanding naturally to kind of understand, oh, where's the highest point of the ball? So if I was throwing a ball with someone else, right, and I was throwing it this way, and you're looking over on the side, you can clearly see where the highest point of my ball throw would be, right? And if you were, for example, catching the ball that I'm throwing, then the same idea happens, right? If you have to adjust, like let's say I'm a terrible thrower and I throw it a little too high or a little too short, right? And then you can naturally understand, oh, I know where it's going to go, right? And I can catch it. And I'm sure for those people who's played sports on teams, someone throws a ball and someone has to catch it, and you're calling out, hey, go closer, hey, go further, right? The fact you can call that out without even guessing, like, or taking a second guess or analyzing where the ball's going, you just know that ball's falling shorter, that ball's going further away. You have this natural understanding of the trajectory of the ball, right? So that's the translation we're going for. Like, can you translate? Technically, that's a parabola. The ball traveling is a parabola. You can naturally do it in a regular sense, but now we have to think of that in a math context. So that whole spiel was about, if you can do that in person, in real life, in sports and stuff like that, you can easily do that here, right? So if any of you have played any sports, whether it's racket sports, tennis, volleyball, badminton, rugby, right? Frisbee, ultimate frisbee, soccer, football, basketball, any of those. If you've played and watched, played, or done any of those sports, and I'm sure there's a lot more that I haven't said, like baseball, softball, that kind of stuff. You know this by heart. You should know this by heart, translation-wise in real life. So let's try to keep it into perspective here. Okay? So now, of course, I went over a ball spiel, but now we're not talking about balls. We're going to a population here. Because we have to also look in context that's not only ball related. So if I were to, for example, show you here, the population of a particular town is modeled by this equation. You're given a quadratic equation here, right? So you're given a quadratic equation, and it says P is the population in thousands, and T is the time in years. Which means t equals 0 and the year is 2000 when t is 0. Okay, so that's what it's saying. So if I ask you here, what is the population in 2000, and I give you the graph, what are you looking for? You look for, once again, like we said earlier, this means that t equals 0. So we're looking for where t is 0. Well, t is 0 over here, and this is our population in 2000, in the year 2000. And so that would be our y-intercept because our t value or our x value is 0. And the population, what is the population here? It's 200, but it's not 200 because it says the population is in thousands. So oftentimes I'll get people writing, the population is 200. And I'm like, no, it's not. It's in thousands. So you have to add another 3 zeros. The population is 200,000, right? In the year 2000. That's what you're looking for here. Okay? So can you have that understanding of also being careful of units? Units are very important here. So let's continue. What point is this on the graph? Well, we already know. It says it here. That's our y-intercept. That should be a no-brainer. Okay? Everyone here should understand that is the y-intercept because x is 0, plus it's where it intersects on the y-axis. Okay? That's our y-intercept. You've used this term for 3 years now. Okay? Y-intercept. And then, what is the population in 2002? Right? So it says, of course, in the diagram, it shows you here. But if we were to translate why that's the case, because t equals 0 is the year 2000, 2 years later would be t equals 2. So this is t equals 2, and we can look at that on the graph, and that would be right here. Okay? Now, of course, you could approximate that, right? You can be like, oh, that's around like 220,000. What's the better way to do this? You can approximate it, sure, you're looking at the graph, but what's the better way for this case? No one knows how to solve it?
Plug in.
Yeah, plug it in. You have t equals 2, you have your equation, plug it in. So the equation is 0.5 t squared plus 10t plus 200. And we're just going to plug this in, right? Plug it in. So solving this here, we get p is equal to 0.5 bracket 2 squared plus 10 times 2 plus 200, right? And so what does that give us? That gives us 0.5 times 4 plus 20 plus 200. And p is equal to 2 plus 20 plus 200, which gives us a final answer of 222. So what's our answer? Therefore, the population is 222,000, whoopsies, in 2002. Okay, and that would be your answer for this question here. Okay. Now, the second thing you want to keep in mind here, right? Yes, if you're given a graph, you can estimate it. But when you're there are exact values you can get from a graph. Like the first question, that is exact. That point is exactly at 0, 200, right? But when you get to these in-betweens and it gets a little bit iffy, you should be plugging it in to solve for it, right? Like t equals 2. Plug it in, solve for your value, right? Do the algebra, do the math, right? That gets you your answer. Then the last question here. In which years was the population 350,000? So I made this horizontal, right, landscape, just to show you the graph a little bit bigger. But we're going to solve it both ways. We're going to solve it both graphically as well as algebraically. Okay. So graphically, where is the population 350,000? Which years? You can type it in chat. Anyone can type it in chat.
Two 2010.
2010. Okay. So we have 2010. Anyone else? Is there another year? So 10 means 2010. Yep. So that's this point here. Ooh, not 1930. Remember, year 0, I get what you're trying to say. Year 0 is the year 2000. So I want you to keep that in mind. Josu's got it. 1970. So Angie, you had the idea. It was minus 30 from 2000 though. So the pointed out here is negative 350, right? You just have to subtract 30 from the year 2000, and that gives you 1970. Okay? So, no, don't worry. No, nothing's embarrassing, right? Sometimes we get answers wrong, right? I mean, you can Angie. It's Angie's first class into our class today. I'm sure more than half the class here can say Mr. Choi has made more than 10 mistakes so far in teaching his lessons over the last 3 weeks. Okay.
Mr. Choi,
So yes.
please explain again how did you get 1970?
Yeah, absolutely. So remember that at t equals 0, right? That's the year 2000. So if we're going negative 30 years backwards, right, from the year 2000, that's 1970. So this is the year 2010, and
So
this is the year 1970.
Okay, so you're just gonna minus 2010 to 30 years? Like that?
From 2000, yeah, you subtract 30 years. Because
Okay.
this is the year 2000, this is the year 1970, this is the year 2010. Now, what if you were supposed to solve this algebraically? So I know there's very minimal space, but let's try to solve this, right? Let's see if we get the same answers. Okay? So here, of course, let's say we graph it, or sorry, we try to solve it. So when it says the population is 350,000, that is telling us, I'll do the side work here. Okay. So what that's telling us is not H of T. The population is 350. Not 350,000, it's 350 because the population in our equation is by thousands, right? So it's 350, and it's asking us to find time. And so we have our equation that we had earlier, 0.5 t squared plus 2, or 10t, 10t plus 200. So we plug it in. 350 equals 0.5 t squared plus 10t plus 200. What do? We're trying to solve for t. And what did we just learn today? Move everything to one side, isolate, right? Everything to one side, and then solve for t. So moving the 350 to the right side, what that's going to give us? Well, that's going to give us 0 on the left. We get 0.5 t squared plus 10t, whoopsies, plus 10t, and then 200 minus 350 is negative 150, negative 150. Yep. And then we can now factor. So common factoring, 0.5. We take out the 0.5, we're going to get t squared plus 10t, that becomes plus 20t, and negative 150 becomes negative 300. So dividing by 0.5 actually doubles everything in the bracket. Now let's factor. Two numbers that multiply to negative 300 but add to 20. Can anyone think of two numbers that multiply to negative 300 but add to 20?
30 and 10. Yep, 30 and 10.
Good. T plus 30 and then t minus 10. And what does that give us? What's our answers then? Setting each bracket equal to 0, we will get t equals negative 30 and t equals 10. Now in this situation, we're allowed to have a negative answer because it represents years, not seconds or minutes or hours. And is that the same answer as the graph? Yes, it's 10 and negative 30. See that? So regardless, if you don't have a graph, you can still solve it algebraically. This is the practice that I would like you to kind of have. Okay? So I want you to get comfortable with practicing this. Okay? Now, any questions about this here, this work here so far? Okay. So now we move on to our last page of our lesson. So I'm going to go through two of these with you. Okay, I'm going to go through two of them with you, and then the rest you're going to try on your own, and then we'll take it up, and that's it for class. Of course, you have your homework questions at the bottom, as always. So each of these rows gives you different pieces of information, and you have to kind of piece them together to figure out all the missing pieces of information. Okay? So you need to figure out all the missing stuff here. Okay? So here, first, looking here, the graphical model of the quadratic function. Well, let's figure out first, what are my x-intercepts? I think those are the easiest. So we have our x-intercepts here. It would be -1, 0, and 2, 0. Those are the two x-intercepts that you can see from the graph here. Once we have our two x-intercepts, that gives us our roots. Right? We can write down those as roots because that's what x-intercepts are. Once we have the roots, we can find our equation because we take the opposite values of these roots to find our equation. And once we do that, we can translate that over to our algebraic model, which is literally the exact copy. You can also multiply this out to verify your y-intercept with standard form, in which you should get this. And looking at the last value, that definitely seems like our y-intercept. Okay? So notice how just giving you a piece of information should allow you to solve for the rest of it here. I'll do the next one with you.
Wait, question. The roots
Yes.
on the equation side. The x equals -1 and the x equals 2. Is it like
Yep.
the opposite? Why is it become the opposite?
When you from the equation,
Yeah.
so to solve for the roots, you set each bracket equal to 0. So if you were to solve for x, you would get x equals -1.
Oh, okay, thank you.
Yeah, so that's why it's the opposite.
Okay.
And then for the next one here, so this time I gave you the equation, or we have the equation here. Easiest way is to solve for the roots, which would be -2 and 1. That gives us our two x-intercepts here. And we can graph them. So -2, 0, and then 1, 0. That's not enough, though. That's not everything that we can kind of use to graph it just yet. We also want our actual y-intercept. So to get that, once again, we copy down the equation over here from the right, because that has not changed. But we're going to FOIL this. So when we FOIL this out, x times x is x squared, x times -1 is -x, 2 times x is 2x, and 2 times -1 is -2. Collecting like terms, we will end up with this, x squared plus x minus 2, and the last value in standard form is our y-intercept. So we can easily just graph that there. Okay? I think that should give you an idea of how the graph should look. It should look something that kind of does this. Just like a rough sketch, right? And we know the vertex should be right here, but because it should be right in between the two x-intercepts. Okay? And so we're going to get that. And that's going to be our quick sketch, ugly sketch of our quadratic equation. I know I draw terribly. There, that's a little bit better. Something like that. Okay, just needs a rough sketch, should be good. So I'm going to leave these two on the screen. I'll zoom out for those people who want to see it while they do the rest, if you haven't printed it. So try the rest of the three, and we're going to take it up. And then once we're done taking it up, that is it for today. So I'm going to give you around 5 minutes to do so, and then we'll take it up. Also, random question to you all. How good are you guys at typing? What's your typing speeds?
I'm probably better than you, Mr. Choi. I'm confident. Better at typing than you.
Oh, really?
Yeah.
What's your speed? What's your speed?
I don't know, but I know I'm good. Yeah.
Okay, because the average person in the world, typing speed is 40. And I'm assuming you're saying you're better than 40. So here, let's do this. I'll keep this here.
You know, Miss Choi, I'm just good like that.
Whoopsies. All right. Oh my God. All right. If you can beat me, that means you're pretty good at typing.
Okay, later today, I'll show you. I'll get better than you.
I'm down. I'm down. If
I'm
anyone
confident.
is curious and they want to try it, I'll type it in. Can you? It's funny because I'm still live streaming on YouTube, so YouTube's just seeing this. We'll have this up. You guys still have another like 2-3 minutes.
SMH, I saw that 80. You were at 91 before. Now you got an 80.
I know, so sad. So sad. All right, you should be finishing up now. All right. That's enough of that. You should be finished at least 1 or 2, if not all, right? You should at least have hit the second one by now, or close to finishing the second one at like kind of like a baseline of how you should be doing these. Okay? So once again, if you have x plus 4, x minus 3, that allows you to quickly find your quadratic. So your quadratic here that you should have gotten is x squared plus x minus 12 as your standard form. Can't really graph minus 12 on this, so we're going to ignore that for now. For the equation here, you have x plus 4, x minus 3, which means our roots would be -4 and +3. In turn, that tells us our two x-intercepts, -4, 0 and 3, 0. Plugging that on our graph, we get these 2 points here. And because -12 is kind of where we're trying to go, we can only assume that the graph looks actually something that does almost like this. Like it just goes straight down. Right? It would be a very deep curve. So it would have to do something that does this. So not exactly the most accurate because -12 would be all the way down here, right? So it would look kind of something like that. But since we can't draw it, we're only going to pretty much draw these two arms here. For the next one, you have your two x-intercepts given to you as values, which means those are your roots. And in turn, once you have the roots, you can find your equation, which are the opposite signs here. And from there, we can also find our y, our standard form of our equation. So we have x plus 3, x minus 5. And so when we expand that out, we get x squared minus 2x minus 15. We also run into that same situation where we can't really draw the y-intercept. And so x equals -3, we can draw that point. X equals 5, we can draw that point. And we're going to also kind of run into this situation. One, two, three, 4, 5, 6, 7. So it would be here. So this would be the vertex here. So we would kind of run into this situation once again where it does this gigantic curve-like thing, and we can't really draw the point. Right? So it would look something like this, and we can only assume that it meets somewhere down here, for example. So something like that, good enough. Right? It's a sketch. It doesn't have to be the perfect, accurate drawing. And the last one here, this one should have been a little bit harder for people. Okay. This was expected to be a little more difficult because of the second root. The first root's easy. That's x minus 4. That gives us our equation there. That's easy. But what about this? What's the second bracket? If x equals 1 over 2, how do we get the bracket here?
Can you do decimal 0.5?
You can do 0.5, but I'd like to avoid that if possible. In the bracket, because we're working with factored form, we do want to avoid decimals in there. So this is where people should have gotten stuck here. This is where I expected people to get stuck. So here, when you get your bracket, yes, we do opposite signs if it's a whole number. But if it's a fraction, just move everything to the left side. So I'm going to move the 2 first, and since it's dividing, that's going to become 2x equals 1. And then moving the 1 to the left side, by subtracting or doing the opposite, we get 2x minus 1 equals 0. And this is your bracket. So you're kind of reversing solving for x. You're kind of just putting everything back to the left side, right? And in doing so, you get your bracket back. So that's going to be 2x minus 1. And so our two roots would be 4, 0 and 0.50. That bracket looks weird, so I'm going to redo it. And drawing that out, so 4, 0, and then 0.50 is here. And let's now find our expanded standard form. 2x times 2x is 2x squared. X times -1 is -x. -4 times 2x is -8x. So that gives us -9x. And then plus 4. So now we actually have a y-intercept we can actually draw. Just like that. Which in turn actually gives you this point to use as well. Okay. So once we have that down, we can kind of sketch an idea of what it might look like. So maybe something like this. Not the most accurate, but that's okay. Because we didn't solve for vertex, right? I'm not asking you to solve for vertex here. You will get a question like that. But for now, in here, don't need to care about vertex. Something that looks like that. So as long as you have that sketch, I was happy. I'd be happy. Okay? All right. Any questions? Cool. So that is it from me today. There's only 2 students that need to stay behind because I just need to speak with them, which is Angie and David. Everyone else, for now, you are allowed to head out. Have yourselves a wonderful rest of the day, and I'll see you tomorrow at 9 a.m. If you want to chill with me and listen to music and stuff like that, you can come by 8:45. Take care, everybody. Have a good one.
Bye, mister.
Bye, mister.
Bye. Have a good day.